That's a good initiative. Thank you.
Hello.
Okay, thank you. Thank you very much. Thank you.
There are still a few seats in the front. Or towards you. Do we have a minutes taker?
Not yet. Didn't get any response.
Should probably get started, eh?
Yeah, okay. Good morning. This is the proposed DINRG meeting, so decentralized internet infrastructure. If that's not what you're interested in, you're in the wrong room. If you want to be here and you can't find a seat, there may be a few empty seats. So can people maybe raise their hand if they have an empty seat next to them? So mostly in the front and then a few in the back. Okay, it's great to see so many of you. Thanks for coming. So before we do anything, we need a note taker for this session. And so we cannot really start without having one. It's a really important function. And the job is mainly to keep track of the discussion. So you don't have to write down everything that is in the presentation. Or you need just a good record of the discussion. Thank you very much, Chris. Okay, so this is my co-chair, Melinda. I'm Dirk Kutscher. And this is the IETF Note Well. So it basically says that if you are aware of any IPR-related topics that come up in presentations or discussions, or you have any IPR that you present, Echo, you are expected to notify us in a timely manner. We have a mailing list. please subscribe to that if you want to participate in the discussion. Do we have an AV person in the room? We have quite some echo here. Okay. Thanks. We normally use this wiki to publish information related on related projects, meetings, and so on. And so this is the agenda for today. So we have a couple of really interesting presentations, and we wow. So projector -1. So we still have one. So let's. First time that happened in a meeting. All right. So we left some time at the end for reflecting a bit on the presentations, but also to discuss a bit the research directions. So let's try to really do this today. Before we start, is there any comment, any need for bashing the agenda, any changes? I think, is Alicia actually in the room? She will, not yet. Okay, she's trying to find the room, I think. Okay, just quickly, if you haven't seen that, we had a full-day interim meeting a few weeks ago at the NDSS conference in San Diego. And so that was actually a pretty interesting meeting, I thought. With presentations from like different backgrounds, so key management, secure online payments, really different ideas, and also quite interactive. So you will find all the material in the data tracker.
And there are links in the agenda slides.
Right. Okay. So with that. Let's start. So Paulo, are you here? Whatever. I have it. Yeah. Mm-hmm.
Hello. I think it works. No? Can you hear me?
Yes.
I can. You can. I think it. Okay, now it works. Okay, so I just bring this set of slides to share some of the ideas that I've been discussing with Dirk about what could be potential use cases and actually some drivers for this group. Just to start with, by decentralized internet architecture, at least in my opinion, is not equal to blockchain. So the blockchain can be a very interesting tool for some of the use cases. But I divide this in use case and drivers because when we were working on this material, we figure out that there are some issues that are actually central, core. Without them, I think this will not work or will be kind of jeopardized, it's kind of centralized. So I call those drivers. Okay? So just to start with, this group is called the Centralized Internet Architecture, but the literature, long time ago, makes a distinction between decentralized and distributed. So I'm not sure if we are talking about the centralization or distribution, maybe something in the middle, maybe for some functionalities we actually mean decentralization, others we mean distribution, but they are slightly different things. Okay, so centralization is a kind of centralized clusters where you have these cluster heads and they have quite autonomy, but they still need to talk to each other, they need to discover it themselves, they need to interact. Okay, while fully distributed is, as you is quite more complex, but stability is quite high, but leads to other requirements like self-organization, etc. So they are slightly different things. So as we go over the slides, you might think that maybe this is more decentralized, maybe this is more distributed. Okay. So why, in my opinion, why we are here? Because we need to. Okay, there is no way to go around it. And this picture, I think, a lot of people know it. So there's a huge amount of traffic, energy constraints, scalability is a problem. We have IoT with billions of new devices being able or wanted to communicate. So how are you going to manage all this stuff? In a centralized way? Not in my opinion. Okay? The internet by itself is decentralized, right? But routing is centralized, DNS is fully decentralized, but based on some issues on daily activity, some of these operations are coming from decentralization to centralization. And this is raising some issues, okay? This is kind of a general picture about topics that I think we could tackle. Some are more wide spectrum, other are more located, but are things like, related with the wireless, local communications, data sharing, data production, IoT, etc. One first use case that I think, at least my opinion, it makes sense, at least from, I worked before in operator and I was always saying we need to make our clients happy, so we need to personalize our services. And if we want to personalize our service, we need to be aware of what the users want, what they need. So we need to have some kind of a mechanism to be aware or gathering information about user behavior, mobility patterns, data that they consume, etc. Most of this information is already available, but this is centralized in some major players. Okay? Another use case is what I call edge networking, not edge computing, but edge networking. That is that there are some operations in a network that can be co-located in an edge because the information that is needed to do the networking functionality is there. The users are moving around these edge devices. Data is coming from these edge devices, so we can actually classify the data when they enter the network, not just redirecting the data to a central point to be classified, right? So self-healing should be done at the edges, so not really at the core. Yeah? So this is some kind of use case that can be useful, for instance, to manage D2D communication or to manage user mobility. Okay? I think until this point I'm not saying anything new, but I'm just refreshing that there are some functionality that we can just do it in a decentralized or distributed way. Okay? For instance, who remembers DeepServe and RSVP, something like that, right? So these kind of things, the classification of traffic can be done at the edges, right? It was done to be done at the edges. So for some reason it's not, because of administrative and the way operators want to control the network. Another issue is, so I call this edge computing. Okay, I can generalize this is not only for IoTs, for anything, okay? For our personal data, even the photos that I take, that I put on Facebook, okay? It will be interesting not to centralize this in an entity, Facebook, Google, Amazon, AWS, but just put it on my personal cloud, okay? What I call here cloudlets. So if everyone has their personal cloud at home, how are these personal clouds being organized, right? If I want to share data with some colleagues and friends, how am I going to do that? Because my data is in my home, right? So how am I going to discover other personal clouds? How am I going to exchange this data? Okay, but this is a kind of scenario that allows to solve some of the problems that we have currently. Is that the people do not own the data. You're losing the control of your data, and you're losing control of your privacy. So by putting your data in your personal cloud, that is decentralized or distributed system, it will solve the problem, right? The other thing is that based on this why do we need decentralization / distribution? Is that because, for instance, you should replace the data where it makes more sense, right? If I have a bunch of users here in this neighborhood in London trying to get information about IETF, why should this information be in a central device somewhere, I don't know where, in the US or something? It should be here, right? So we should replace the data here. If we do not replace the data, maybe we replace the computational functions, right? So there are lots of distributed functionality that can be distributed in this kind of scenario. If you go more into the wireless part, because these are 3 examples, there could be more. Like I said, this is not an exhaustive list of use cases, it's just food for thought. Okay? I selected these ones. In the first one, named based opportunistic communication, we can generalize this and call it just opportunistic communication. It means any communication over wireless network, multi-hop wireless network, right? If you do that, how do you do, for instance, your ID verification? If someone wants to contact you, how do you know that this person is really who they are? Okay, a certification authority, but you don't have access to the internet. So how do you do that, right? So that's a problem. Cooperative relaying is also something that by nature is centralized. Also, it's not wide spectrum is located, but it's decentralized. Something that is important for operators is multi-cell wireless provisioning that can be local or more broad, in the sense that we need to have a clever way to allocate spectrum, right? And this normally is done within an operator, not multi-operators. Okay? And if you go to the idea of femtocells and people have their own facility at home, then this can be something to look at. Okay. Oops. Frozen.
Try again.
Okay. So before coming to this slide, this slide I tried to think, okay, in all these use cases, and I had others in my mind that I didn't place in the slides because of time constraint, what are the issues that are always present that you should look at if you want to do a decentralized / distribution? The first one that actually is not here because I think is obvious is the ID management. Okay? If I want to start communicating with someone, I have to make sure that this person is who they really is. Currently, we use certification of authentication, but in some scenarios, that may not be the most interesting thing. For instance, in name data networking, is used this hierarchical naming scheme where the data packets are signed and signatures are verified in a chain. So this is an example of a kind of decentralized approach for this scenario that actually can be used in an opportunistic network by itself, because I don't need to go to a centralized server. I can just ask for the keys to my neighbors, keys for the node keys. Okay. So based on that, I think, at least in my opinion, and I share this also these thoughts with Dirk. This is kind of raw thoughts, but I like these 3: trust management, cooperative incentives, and consensus. Why? Because if I know who I'm talking to, if I know everyone in the room, first one, I will, even if I know all of you, I will not communicate with all of you at the same level. I have several different trust levels with each one of you. So I'll use this trust level to set up my communication. So this is why trust communication is quite important. And this is based on reputation. This is based on crypto IDs that are just going back to the ID management. But this may not scale, because if I try to come up with trust of circles on the fly every time where I'm different locations, it's going to be like a nightmare. So maybe I want to go to cooperative incentives, in the sense that I want to communicate with people or exchange data with sensors that I actually do not trust, but I have some incentives to do that. Okay, and with this I can go in things like virtual currency. So I have to get some reward to do something. If I want to share my bandwidth with someone or to share my data, I need to get some reward back. I don't trust you, but if you give me some reward, then I give you what I want. Okay, this idea of virtual currency is from 2011 or 2012, much before this buzz about blockchain, but this could be implemented that way, in a decentralized way, because this idea of this virtual currency was not centralized, was centralized. Finally, even if you are in a very, let's say, trustful, or if you have the incentive to cooperate, there are lots of situations in the decentralized environment where you need consensus. Imagine an operator network where you have different network functionalities distributed that actually are doing competitive things. One network function wants to save energy, but the other wants to do load balancing and does not care about the energy. How does that work? So if this can be done by just having an orchestrator, centralized one, that's the classical approach. If you want to do it in a centralized way, you have to have a consensus algorithm. Something like swarm intelligence, algorithms to do that. Okay? Then that's it. Just to rephrase, okay, this is just a set of food for thought. If there are some questions or comments, if I said something that is really crazy or stupid, just say so.
Yeah, any questions?
Thank you.
Thanks, Paulo. Where's the clicker? Yeah, so next is David Messier.
Hi, thanks. So today I'm going to talk about the Stellar Consensus Protocol, which is a draft that we've submitted the 0th version of. And I've talked like a year ago, I guess, in Chicago. I talked a lot about kind of like the motivation and the model, and in the interim meeting we had a bunch of kind of motivation. So this talk is really about getting into like how the protocol actually works. How do I?
Try again. Sorry.
Okay. So SCP is an open Byzantine agreement protocol. So the idea is you could sort of have the whole internet agree on reach consensus on things.
Whoa.
And,
Yeah.
I think you kept pressing.
Okay. I might just hold this so that I'm not tripping over the microphone stand. And I keep pressing that. Okay, and so obviously the big problem in an open system is that traditional Byzantine agreement protocols assume sort of majority voting or supermajority voting, and that completely breaks down in an open system because you have these Sybil attacks where the bad guy joins 100 times and then can kind of overwhelm the number of good guys. So the idea in SCP is that instead we're going to determine quorums in a decentralized way based on the participants' trust. So we say, like, if capital V is all the nodes in the world, then for every individual node V that's participating in this protocol, there's some set of sets that V would accept as a quorum. We'll call them like little q1 to little qn here. And so we'll have this capital function q of V, which basically says all the sets that that V would accept as a quorum. And we'll say that V has to be in each of these little q's. But the thing is, each of these little q's is not actually a quorum. It's what we call a quorum slice. Right, and a quorum has to kind of transitively satisfy the dependencies of all its members, right? So the kind of key definition in this whole protocol is that a quorum is a set of nodes that contains at least one slice belonging to each of its members, right? Every V in the quorum has some quorum slice Q that is a subset of U. So so this works for consensus, but like requires an assumption. And the assumption is that there's sort of transitive overlap of trust if you follow the people's dependencies. And there's some analogies to kind of build an intuition for why this might work. So one is if you consider transitive reachability on the internet, right? Imagine two networks that both speak, you know, IPv4 and IPv6, and they're all equally sort of RFC compliant, and but they're not reachable. No node on the left network can talk to any node on the right network. Well, they both obey the internet protocol, but one of these networks is going to contain Google and Amazon and Apple and Microsoft. And so like, we're going to say, well, Stanford's on that one, like that one is the internet. And the other one, even though it speaks the same protocol, that's not the internet. So that's just the notion which we're trying to capture this overwhelming consensus about something without centralized control. It's just that everybody kind of agrees on what the internet is. Another example would be kind of the rough agreement on who constitutes a tier 1 ISP. If you asked everybody in the world, who are the networks that you think you would be glad to get transit from or peer with, right? And then you sort of transitively follow that, there will be a large amount of overlap, even if everybody doesn't agree on what a tier 1 ISP is, right? And similarly, every browser doesn't have exactly the same set of certificate authorities, but there's a lot of overlap in this, right? So these are the kinds of things properties that we can exploit in order to get global consensus. So just to kind of walk this through with an example, here's 4 nodes and their quorum slices. V1's quorum slice is V1, V2, V3, and V2, V3, V4 have this quorum slice of V2, V3, V4. I'm also visualizing the other members of a node's quorum slice with arrows. And to keep things simple, each node has only one quorum slice here. So here you can see that V2, V3, V4 is a quorum because it contains a slice of each member. But V1, V2, V3 is a quorum slice for V1, but it's not a quorum, right? Because V1 says, well, I would believe a quorum with V1, V2, V3. But V2 and V3 are saying, well, we'll only believe a quorum if V4 is also a member. So the smallest quorum that includes all of these is the set of all nodes in this example. So, of course, we have to actually represent quorum slices in this protocol. So, mathematically, we could choose, any sets of nodes as quorum slices, but we want to be able to represent this compactly. And so what we do, which seems to capture a lot of real world examples, is we have this kind of hierarchical thing where a node is named by a public key, and we have crypto agility, but for now we're using ED 25519 because that's a good signature algorithm. So every node has a public signature key, and then this we're using XDR to specify the protocol. So a node basically specifies an SCP quorum set as a kind of K of n threshold specification, saying I will believe any K of these n nodes where any individual node is also an SCP quorum set. So you can have, or is either a public key directly or an inner set. So basically you could say, I want to believe, 3 out of the following: node A, public key B, public key C, or 2/3 of public key D, E, F, or and so on, right? And you can go 2 levels down. So this makes sense. We have IBM. In our current deployment of this, IBM is running like 8 nodes around the world. So you might want to say, well, I'll trust like 3 out of these 4 companies, but one of them is IBM, and I'll wait for 6 out of 8 nodes from IBM or something, right? Figuring that those would be correlated in terms of maliciousness, but you want to be able to tolerate one of IBM's data centers being down. Okay, so the key idea in this protocol is that nodes vote for statements by issuing these signed messages, but every vote has to specify the acceptable quorum slices to the voter, right? And so as you collect these votes, you learn of a quorum because you see a vote and you see what that node's quorum slices are, and then that kind of expands the set of other votes that you need until you've got a closed set. And obviously a well-behaved node is not allowed to vote for contradictory statements, and we'll get to like what you can vote for later on. But as you're collecting these votes, there's 2 important thresholds that have meaning in the protocol. The first is if you have quorum thresholds. So if a node V sees a bunch of nodes all voting for statement A, and that set contains a quorum that includes V, then we'll say that statement A has reached quorum threshold at V. Or you could also be in a situation where node V notices that every single one of its quorum slices contains at least one node that has voted for some statement A. And then I'll say we've reached blocking threshold, because basically V will never see, assuming these nodes are honest, V will never see a quorum vote for a contradictory statement, because that quorum would have to contain one of its quorum slices, which would contain a node that's voted for A. Okay? And so I'll say that a node V ratifies a statement A if the statement A reaches quorum threshold at V, right? Meaning V is in a quorum where every single node has voted for this statement A. And I show in the white paper that the proof of the protocol that the system will not ratify contradictory statements as long as you have this property of quorum intersection despite ill-behaved nodes, or QIDIN. In other words, if you delete all the nodes that deviate from the protocol, kind of conceptually from everybody's quorum slices and from the set of nodes, every two quorums still have to intersect. And if they don't, well, then no protocol could actually guarantee safety. Now, this isn't really a particularly intuitive notion, this idea of conceptually deleting the ill-behaved nodes. But the point is that it's a necessary property to guarantee safety. And so if the protocol can guarantee safety whenever this holds, then that means it will also imply any other model. In other words, this means it's kind of optimal in terms of safety. So you could kind of think of this if you were presenting an encryption algorithm, and someone might say like, well, your encryption algorithm is secure against an adaptive chosen ciphertext attacker. Like, that seems like a weird kind of attack. Who's going to pull that off? But we do that because we think that captures all the other kinds of attacks that might happen. So the idea is that this weird requirement is supposed to capture any other like weaker failure model that you might have. Okay, so the way these vote messages happen is that nodes send around these statements and paired with signatures, and the statements themselves contain the public key of the sending node. The slot index, that's because you agree on a series, you run this protocol a series of times to kind of agree on log entries, if you will, if you're updating a state machine. And then it includes the SHA-256 hash of the quorum set, so that, because these don't change that often, so you don't want to communicate the whole thing. It's more compact just to name it by a hash, and you can just request from the sending node what the preimage of the hash is if you don't happen to have it cached. And then there's a statement in which you pledge a bunch of votes, and we'll get into what these statements are in a second. But basically, the big picture here is that you're sending around these nodes, you're sending around these votes along with quorum slices, and several things will happen. So let's say you're trying to decide between some statement A and its opposite, not A. Well, in the beginning, nobody has voted. Right, so everybody could vote for A, or everybody could vote for A bar. So we'll say that the system is bivalent, right, because either outcome is possible. Then at some point, maybe some node ratifies a statement A, and at that point, assuming you have this quorum intersection despite ill-behaved nodes property, no node will ratify a contradictory statement A bar. So in a sense, A is the only possible value that the system could agree on here. And if every node learns that in fact the system is avalent, then they'll basically decide that, well, we've agreed on A because we know no other possible, we're not going to vote on any other possible value. But at any point along the way, you could potentially get stuck, right? Like, for example, a node that accidentally voted for not A, even when everybody else votes for A, will not be able to vote for A, so it will not be able to ratify A, right? Or it could be that a node kind of unknowingly ratified A, but then some other node in its quorum that also voted for A crashed after voting for A, and the vote message got lost or something. So basically, it'll never learn that in fact the system is avalent. So the result is that we're kind of stuck. Okay, so an important question is, how do you actually know? Just because you've seen, say like a quorum vote for A, if like say there's T nodes in your quorum, great, you know the system's avalent, but how do you know everybody else is going to learn that the system is avalent? And the traditional solution in Byzantine agreement protocols is that you say, well, look, maybe there's a bunch of nodes here that say that they all saw a quorum vote for the statement A. And that set is large enough that it incorporates the entire intersection of two different quorums, like quorum A here on the left and quorum B on the right. And therefore, if they're all malicious and all lying to you, then they could be driving these quorums into divergent states anyway. So you might as well, you can kind of believe them with no loss of safety. So this turns up a lot in PBFT, for example, like one of the more popular Byzantine agreement protocols. That's a centralized protocol. Unfortunately, this completely breaks down in this open model, because what happens here is that from, say, this node's point of view, Vn-1, it says, well, I realize that if these nodes are all lying to me, I might be driven into a divergent state from quorum A. But the problem is quorum A might be some kind of weird Sybil attack here. So whereas in the centralized case, we care about failure as a property of the whole system, now in this decentralized case, we have to care about failure as a kind of per node thing. And each node has to kind of look out for itself and say, you know what, I'm not willing to believe anything unless I'm actually a member of the quorum that voted for this statement. So, so on the other hand, okay, so there's a couple problems here, right? To kind of motivate why we need to do something fancier than just a straight up vote, right? How do you agree on a statement after you voted on it, or after you voted against it? And you know, how do you know once you've agreed on a statement that, you know, everybody else will agree to that statement? So suppose that you're node V1 and you notice that in every single one of your quorum slices, there's another node that's willing to say that the system is avalent, you know, that it saw a quorum vote for A, or for whatever reason it thinks A is the only possible output value, right? So in other words, this statement that the system is avalent has reached blocking threshold for V because it's in every single one of V's quorums. So at that point, either it's true that the system really is avalent, or V1 is not a member of any well-behaved quorum, so it's not going to be able, it's not guaranteed liveness. It may be, the bad guys may be able to get it stuck, so it can't make any progress, right? So let's define a slightly more permissive notion than ratifying a statement, which is what it means to accept a statement. And we'll say that it's node V accepts a statement when that statement is consistent with history, and one of two things happens. Either the statement, I voted for A, or I already accepted A, reaches quorum threshold, meaning it's in a quorum in which every node has either voted for A or accepted A, or the statement of I accept A has reached a blocking threshold. And this second criterion is what lets nodes accept statements that they've voted against, right? But we're not done yet, right? Because the problem now is by weakening this, we've gotten ourselves into a situation where nodes, even if you have quorum intersection despite ill-behaved nodes, so you should be able to guarantee safety, you could have well-behaved nodes that accept diverging statements, which is bad. And also, you know, we have some nodes that previously couldn't ratify a statement that can now accept it, but there's no guarantee that all the nodes will be able to accept a statement, even if you have. So the solution here is that we have to hold a second vote on the fact that the first vote succeeded. So basically, you have the second vote on the fact that you've already accepted the statement A. And this solves both of the problems on the previous slide. It solves safety because now we need quorum threshold for this ratification. There's nothing about blocking threshold here. It also solves the problem of honest nodes, you know, in an honest quorum being unable to accept a statement that other nodes have accepted. Why? Because there are nodes in a well-behaved quorum that might vote against accepted statements, but they won't vote against the fact that those statements were accepted. So in fact, one of the things that I prove in my white paper is that if you have a single node in a well-behaved quorum that confirms a statement A, then eventually all the nodes will confirm the statement A. So that gives you this notion that yes, we're done, the system is actually going to agree on A. So basically, this is like the main building block of the SCP protocol here. It's this federated voting process where you start in kind of an uncommitted state, and then there's some statement A that you think is valid, so you vote for A, and then the statement of like I vote for A or I accept A reaches quorum threshold, then you accept A, and then you have this second vote where you confirm A, and at that point you can kind of assume that the system is confirmed, that A is true without sacrificing safety or liveness. Right, and conversely, of course, you could vote against A, but then if there's this blocking threshold that accepts A, you can still accept A, and you can still go on to confirm A. And the knowledge you have is if you locally confirm the statement A, then you know that and you know that the system is not in some terrible state where you don't have quorum intersection despite ill-behaved nodes, and where you actually have a working honest quorum. Then you know that kind of all the other good nodes will also accept this statement A. So. So with that said, once you understand that building block, the rest of the protocol should ideally at least make some intuitive sense. I know this is a lot of material to plow through. So the first phase of the protocol is that you actually have to decide what value you actually want to agree on, right? And so for that, what nodes do is they vote to nominate particular values. And for the purposes here, a value is basically like just an opaque byte string, right? So they send these nomination messages around that contain votes to nominate particular values, and also contain lists of values that have already been accepted, meaning they've progressed to kind of the second stage of the federated voting protocol. And so basically, initially, what nodes do is there's an optimization where not everybody initially nominates something just to make it more efficient, but conceptually everybody could nominate a value. And then what's important is as you receive values, you renominate those values if you see other people voting for values. So you keep sort of happily nominating more and more values until such point as you start accepting values because maybe they reach quorum threshold or they reach accepted threshold, or they reach blocking threshold in the accepted vectors. And as you accept values, you move them from votes to accepted, and you keep broadcasting until one of these accepted values reaches quorum threshold. And then you've actually confirmed a value as nominated. And at that point, you stop voting to nominate new values, but you keep renominating the old values that you've been nominated. So eventually you might actually have one or multiple values end up as confirmed nominated. So basically what happens is these nodes, they start nominating values. Like here, let's say they're nominating sets of transactions. So they keep propagating these things until such point as one of these values is confirmed, like maybe TX3 is confirmed nominated here. Then eventually, everybody will converge on the same set of nominated values because you've stopped introducing new values to nominate. And then you can deterministically combine all the nominated values into some composite value X. So if they're sets of transactions, maybe you want to take the union of all the sets of transactions, or maybe you want to take the set with highest hash value, or if you want to get fancy, maybe you want to use verifiable random functions and some other phase to pick them. So it doesn't matter as long as it's deterministic and everybody picks the same output value. And what's nice about this nomination protocol is that all nodes are guaranteed eventually to converge on the same composite value X. Now, there has to be a catch because we know that there's this FLP impossibility result that says you can't have a deterministic consensus protocol that's guaranteed to terminate in an asynchronous network. And the catch here is you don't know when the convergence has happened, right? So you take your best guess at, okay, we've probably converged on X, but it may be too early, and so you need to do something to guarantee that this will still be safe. And so for that, the protocol moves to kind of a second phase that involves balloting. And this, if you've seen Paxos, this is kind of a generalization of Byzantine Paxos. So what is a ballot? Well, a ballot is basically a pair of a counter and a value, and the idea is that initially the value you'll choose will be whatever the output of your nomination protocol was. So these ballots are totally ordered, and the counter is the more significant one. So 1 comma anything is less than 2 comma anything, and then the value is the tiebreaker. And nodes are allowed to vote to commit and abort ballots, but not both. It's contradictory. You can only vote one or the other. And if ever the federated voting confirms that some ballot B is committed, then it becomes safe to output the value in X, which I'll write B.X for the value in a ballot, and B.N for the counter in a ballot, right? So this is how we finish, and we actually choose a value. So there's an important invariant, though, which is that you can't vote to commit a value unless you first prepared the value, the ballot. And what does it mean to prepare a ballot? It means you prepared a ballot B if you've basically confirmed a whole bunch of abort statements. Namely, you've aborted every ballot B old that is less than the ballot B and that has a different X value, right? And so basically, you first have to prepare B. Then, if you succeed in confirming all these abort statements, you can issue the you can actually vote to commit B. How am I doing on time? Am I out of time? Or?
If you
You've
could-
got a minute. Yeah.
Okay, so so basically, you work through these two phases of the protocol where you have to prepare ballots, and then you vote to commit ballots in this confirm message, and then once you've committed ballots, you can output this externalized message, which helps other people who've fallen. You're done at that point, but you issue this final message that helps other people who may have fallen behind quickly catch up, because you can kind of say, like, actually, it's as if I don't have I have a trivial quorum slice because I've already seen my quorum, so you don't even need to worry about my dependencies. You know, I guess now that I've laid the groundwork, maybe at the next one I can actually get into more details of how the protocol. So here's the balloting. You prepare some value, and then you confirm the value, and then you can output X. But if your nomination didn't converge, then this is still safe. You just might have to go through multiple ballots. Okay.
Oh, thank you, David. Questions? You have to go up to the microphone.
A couple of notes, having read the RFC.
Can you state your name?
The description of quorum slices in the draft. Sorry. Nick Johnson, Ethereum Foundation. Start again. The description of quorum slices in the draft was quite opaque, but your description in the slide was quite clear. So may I suggest rewriting it a bit? Because it was
Point
a lot
taken.
easier.
Yeah, the deadline was. I didn't realize how early the deadline was. I want to improve the draft a lot. So.
And it also wasn't clear to me how you encode or decode the quorum slice representations with the nested sets. So an example of here's a nested set and here are the quorum slices it translates into would be really useful.
Yeah, it's so that's in the recursive data structure. It's just using XDR. So XDR accommodates recursive data structures. So you can just have a quorum. You can have a vector of quorum sets inside a quorum set.
Right. What wasn't clear to me, though, is how you translate from that into the aforementioned set of quorum slices, because the quorum slices is a list of lists of nodes.
Right.
And it wasn't clear to me how you get from one to the other.
Right. So you just have to satisfy any K. You have a threshold, and you have to have that yourself plus that many of at the current level. So you need to either that, like, for example, if your threshold is 5, then you could have 3 nodes in the validators set, do it plus 2 recursive SCP quorum slices. That would reach 5, basically.
Right.
So
Okay.
I just need to describe that better.
Yeah, or just an example of
Yeah.
these would be valid slices from this representation.
Yeah, that's a good suggestion.
And I thought also some motivation on just the overall mechanism being described in informal terms ahead of time, like you
Right.
did here, would have made it easier to follow.
Okay.
So
Thanks. Good suggestions.
By the way, we have some blue sheets going around. So if we want to have a bigger room next time, please make sure you sign them. Yeah. So who hasn't signed the blue sheet? Just pass them around again, please. That's maybe easier.
Okay, so Paulo Mendes. Just for clarification, I have 2 issues. I think if I got it right, you have some assumption about trust. So you assume that the nodes trust each other, right?
I assume that, I assume that basically that nodes depend on one another. Nodes say, like, I'm not going to agree to something unless, like, Google and Amazon and, like, VeriSign do, because I think those are all important, or 3 out of these 4 companies or something. And what I assume is that if you sort of take the transitive closure of these trust dependencies, that there will be overlap. So you take any 2 people, they might not know each other, but if you sort of translate, take all the people they depend on, that there'll be some set of, like, companies in the middle that everybody depends on.
Okay, so you correlate trust with dependency, codependency between the people.
Yeah, I mean, trust is kind of a weird, you might not trust these people. What you trust is the conjunction of a bunch of people, right? I might say, like, what I trust is actually the conjunction of these 3 big companies plus the EFF and the ACLU, right? Like, once all of those organizations all say the same thing, like, I'm willing to actually, that's what I'm willing to trust. And so I depend on each of these individual ones. Like, they could potentially hurt my liveness, but I'm not going to believe something unless they all tell me that they're on the same page.
Okay, so I'm asking you because of the applicability. I'm trying to understand the applicability of the applicability.
Uh-huh.
It seems that you need kind of offline agreement before applying this protocol.
So each participant needs to kind of configure their validator, their node that's running this protocol, to have a quorum slice, to have one or more quorum slices. That's
Okay.
right.
Okay, got it. The other question is about the protocol itself.
Mhm.
So if you need a protocol that allows these software agents to discover each other and to synchronize their state and to do some kind of negotiation, do you think about using GRASP from the ANIMA working group?
To use which?
GRASP protocol.
Maybe we should. So we don't. This is sort of agnostic as to the overlay network protocol, but you obviously want some kind of peer-to-peer multicast because you end up kind of broadcasting a bunch of these messages around. And like right now, what Stellar does is not especially intelligent. Like it's sort of more reminiscent of Nutella. It's like just a flooding protocol. So you may get multiple copies of the same message. And so if there's like work in the IETF or IRTF that we could use off the shelf as an efficient multicast, peer-to-peer multicast protocol, that would be useful. So is there? You think we should, or is there, or you're saying?
In the ANIMA working group,
Uh-huh.
for a long time, they are trying to come up with a protocol that is able to allow autonomous software agents
Mhm.
to discover themselves and to set up infrastructure to do this kind of. One use case could be this consensus. So they are able to discover themselves, they are able to synchronize their state, and they are able to negotiate some arguments.
Yeah.
This negotiation of arguments could be this consensus. Actually, could be this algorithm. That's what I'm saying.
Although that, I feel like we might be targeting like slightly different. Like this is a protocol that, like, I'm imagining SCP is something that you would run probably not on like a bunch of IoT devices or something, but rather it would be a way of, having like all the CT logs, like authorities, like combined together and like have like a single log or something. So it'd be like sort of known, trusted, like available entities on the internet who would be participating in this.
Something to look at.
Okay, cool.
Thank you.
So David has kindly started writing this draft. So it would be good if you're interested look into that. I think you're planning an update on this.
Soon,
Yeah.
I plan to make it easier.
Fantastic. Okay, great. Okay, let's move on. So I think, is it Colin who's doing that, or?
Yeah, Colin, I sent you a message just a little bit ago. If you're out there and listening, you need to join the mic queue in MeetEcho, and we can let you in from here.
Not anymore.
But we can, we've got the slides here, so.
Good.
So
Hello.
hi, Colin.
Hello.
Hi, Colin.
Hi. I'm glad you guys can hear me.
Yeah.
Sorry, I'm trying to figure out this software. How do I change the slide?
Tell us.
Yeah.
Okay. Yeah, so I'm Colin Mann from Stanford University, and on the line with me, sorry, can you go back one slide to the title, please? So on the line with me is John-Luke Watson, also from Stanford, and Sydney Lee from the EFF. So today we're going to talk about distributed authenticated mappings. So what are authenticated mappings, you may ask? So next slide, please. So essentially what we did was we looked at what's currently broken in the internet and the solutions that we have. So the 4 problems we looked at, the first one is how do you send private conversations over encrypted email? How do you have secure internet for small websites? How do you have secure domain lookups, like domain resolution, and just how do you have secure identity verification? So next slide, please. The solutions that we have right now in the current internet is trusted key servers for encrypted email, HSTS policies and preload lists for secure internet, and DNSSEC for domain lookups, and CA trust chain for and certificate transparency for verifying identity. Next slide, please. But these all have their own problems. So with trusted key servers, you can man the middles. HSTS is susceptible to downgrade attacks, DNS poisoning. There's a single point of failure for CA trust chains. And what we saw here is really that there's kind of a need for a general authenticated mapping. So in the first case, what we really have is a public key mapping from an identity to a public key for encrypted email. In the second case, it's a mapping from an identity to a policy, so like a domain to a policy. In the third one, it's domain name to IP, and then in the fourth one, it's a domain to a certificate. So really, like the underlying problem here is all about mappings. So next slide, please. So the idea is like whether we can derive a scalable solution that's going to work for any kind of mapping. So ideally, we want it to be distributed so that there's no single point of failure, and we want kind of like a global state database. So some of the properties we want. Can you go next slide? So some of the properties we want are we want append only properties. So we want to be able to keep track of all the things that are happening on the mappings, so that we can have a record. And we also want well-formed transitions so that we can essentially keep a valid state in the database at all times. And the idea is that what we're building really for authenticated mappings is kind of like a framework or a platform that we can put on top of a consensus protocol to make it much easier to solve problems that involve mappings where like the transitions need to be authenticated. Can you go next slide? And then the last thing is that it has to be transparent. So we kind of took a leaf from like Connix, for example, where you have to be able to see exactly what's happening, and everyone has to be able to see the exact state of the mappings at all time. So looking at the layers that looking at like how we want to design this, the first thing is that we want to bootstrap our network from existing PKI. We don't want to just invent something that's like completely separate, and we want to be able to use existing trust networks. So next slide, please. So the idea is like you should be able to actually use an existing certificate in order to certify a mapping in this authenticated mapping system, and then maybe from there we can use like new keys or like keys on this new mapping to enforce transitions afterwards. So in terms of the actual consensus protocols that run under it, we evaluated a couple different options. The first one is just like the Byzantine fault-tolerant cluster. The problem with that is that the participation is limited, and a uniform set of incentives undermines the security. So yeah, and then the second thing we looked at is like maybe building on top of like a proof of work or proof of stake system. The problem with that is like it's open membership without really accountability, and like the trust is tied to hashing power or available resources. So it's possible that like someone with like a lot of hashing power could take over the system. So what we really wanted to look at is actually can you next slide please? It was actually like some from a federated Byzantine agreement. So we actually worked with David Nazirez as well, the previous presenter, to talk about possibly overlaying our framework on top of the Stellar consensus protocol, because Stellar is kind of based on existing trust relationships, and it's the kind of protocol that we're looking at where we can basically take an existing trust network that already exists in the world, plus some kind of like existing public key infrastructure, and use that to bootstrap our our authenticated mapping system. So right now, I think Federated Byzantine Agreement seems like the best choice for a mapping system like this. Next slide, please. So in terms of actually how to create a framework that would be easily usable and be able to support these well-formed transitions, we thought through kind of like how a protocol or an interface would look for for this kind of transition. So next slide. So in order to do that, we actually went through 2 examples and thought about how the mapping works and what you really need in order to provide like a good mapping and like what kind of semantics are needed. So the first example is PGP keys. So like for example here, if you're doing email encryption, what you want to do is be able to map aliases to public keys. So aliases could be like email or a domain is the 2 that we have in mind right now, but essentially you need to be able to map that to a key so that you can encrypt information to it. So on creation of the entry, what we really want to do is check that some kind of like domain authority can verify the identity. So this is like, if my email is colin@stanford.edu, in order to actually create an entry to map that email address to the key, I want like Stanford to sign off on my initial entry. And that's kind of how we do, like how we want to do like the bootstrapping so that we can use existing infrastructure without having to kind of just like that's how like we can initially verify the identity. And then afterwards, what we want is that every time the entry is updated, we want either like the previous public key to sign, or maybe like N of M trusted parties to sign to approve an update. And the idea behind that second one is like maybe we want to do recovery or something. And then the second thing is binary hashes. So right now, mapping download URLs to their hashes or like their checksums is also something that you want to be like authenticated, because when you download a binary, you don't really know if someone's like changing your page in the middle to like show a different checksum or something. You need some kind of mapping from the URL to the hash. So for this kind of semantics, what we want is again, on creation, we want the domain hosting the URL to sign the entry, and then on update, what we want is like the same domain signing the update. So looking at this, next slide, please. Some observations that we had were essentially that on creation and update, we want some kind of validation based on local state. We want some kind of external authentication to bootstrap this. And then we have this kind of like idea of ownership, where there's going to be some person kind of like who owns an entry and is able to set semantics for like how the entry will be updated afterwards. And then also some kind of like recovery or threshold cryptography sort of operation in there as well. So next slide. So what we came up with is essentially a structure where you can actually create mappings in the system. So each mapping will be able to have two validators. Two sets of validators. So you have creation validators and you have update validators. And essentially all creation validators need to pass in order for a new entry to be created. And each validator inside it has operations where one of the operations needs to succeed in order for the transition to succeed. So the idea is like actually each node in the consensus layer. So for example, if we were running this on Stellar, each node would look at the update and run these validators to make sure that whatever entry is like being created for a particular mapping is valid before voting yes on the transition. And in that way, we can actually always maintain the fact that everything in the cluster is valid, and like any lookup for a value is going to be valid. So next slide, please. So one example here is like if like one of the mappings was like PGP keys, right? Email to PGP keys. Then the mapping would be like email PGP is like the name of the mapping. And you can have here like in the create validator, you have one operation is like the domain authority signature, like that's what you need to create the entry, and then in the update validator you have like the signature from the previous key, or n of m signatures that are specified inside the operation itself. And you can see the struct down here that we came up with as well. Next slide. So in terms of like what validators are, I talked about this a little bit earlier as well. Essentially, it's a collection of operations that are enforced. So you can actually there's a link to the GitHub repo at the end of this presentation if you guys want to go through and take a longer look at what the interface looks like. Yeah, so like here you can see that there's essentially like 2 operations in there. Next slide. And in terms of like what operations there are right now, we have a really limited set. But we have, for example, like CA signature is going to be like a signature that where like a certificate chain is provided and a signature using the public key inside that certificate is used. And then you have like op owner signature, which is like the whole concept of whoever owns that entry. So like each key in that mapping is going to have some kind of domain authority associated with it. Like if you're mapping email to a key, the domain the domain authority is the domain of the email. If you're mapping a domain name, then obviously the authority is going to be that domain. So like the idea of this mapping is like there's always going to be some kind of like owner who can verify. So that's the owner signature, and then like n of m signatures as well. And then here's an example of an entry update. So it's also for PGP keys. So I can like update my my email mapping with a new public key. And the idea here is like there are also update operations that I can put in. And then the idea is like some of the operations that are set on the mapping are going to need to be parameterized by the entry itself. So for example, whoever's creating the PGP key mapping doesn't know like which n of m signatures I actually want to have for my entry. Like that should be something that I'm able to set myself. So the idea here is like you can actually put in parameters. Like I can say, okay, well, I trust Jean-Luc and Sydney. Like they like if two of two signatures from both of them are present, then like that's also a valid transition. So here, like the actual operations are set by the mapping, but the parameters are provided on like an entry by entry level. Yeah, next slide. And another thing here is like some of you guys might be thinking, why like you could also just like implement this in a smart contract, like for example in Ethereum or something. But the idea behind having this mapping abstraction or mapping framework is that well, first of all, it's really easy to implement on top of a consensus layer because you don't need to develop like as comprehensive of like a contract language. You don't have to worry about like looping and gas and stuff like that. The second thing is like it's easy to use because all the operations are already well defined, so it's easy to create a new mapping depending on your use case. Like maybe I'm writing an encrypted messenger client and I want to create a public key directory for my users or something. It's like really easy for me just to define what operations I need. It's less error prone. So in terms of like when writing smart contracts, it's really easy to actually write in like subtle bugs that could be exploited. And then the fourth thing is like it's really designed to be bootstrapped off of existing trust infrastructure. We really want to make sure that that it's not just like an isolated system that is just like running on the side without having any interactions with the existing trust infrastructure in the society. Next slide. Yeah. So do you have any questions?
Thanks a lot. Thanks a lot. Yeah, people coming.
Hi, Nick Johnson, Ethereum Foundation again. I'm just wondering, what is the model for adding new mappings? Would the set of mappings be defined at deployment time that require a system-wide upgrade, or can anyone add a new mapping that uses existing validators?
Yeah, so the idea is that anyone can add a new mapping. And we're working on a form of versioning as well, where if we introduce new operations, and you can actually create like a new version of your mapping that uses those.
Okay, so how do you prevent abuse of the system in that case?
You mean in terms of like someone who's just like spamming with too many, like creating too many mappings?
Precisely, yeah.
I think that's something that we still need to think about. It's still kind of like in the early phase. Like maybe we will restrict it a little bit, but we're also open to any ideas on that if you have.
Cool, thank you.
Hi, Michał Krum from UCL. I'm just wondering, there is probably, there is like name coin for identities and domains. And do you see there is something missing in their system, or what's the delta between those mappings, or what you want to do and their system?
I think the idea behind these mappings is that it's like it's a much more generic mapping. So it's not necessarily just like identity to key or like domain name resolution. It's like a much more general framework for creating new mappings.
Okay, thank you.
More questions?
Anything in the chat room?
Okay.
Is Shahar here?
Lisha's next. Lisha's next.
Okay, Shahar's,
No, I'm just.
So professors are known to misbehave. Normally we make the lecture slides either during the breakfast, otherwise we use like 10 years old slide stack. And this time is different from anything else that I literally finished when I was sitting there on the floor. So I'm a little nervous, and this is not mine.
no, yeah, it's a confusion about this.
Yeah, no.
Should I use my own laptop?
I'm just getting the slides right now. So
Okay.
if you have it right here, it would be easier.
It'll be easier.
Yeah.
So I apologize. But you'll be after each other. Oh yeah, we can have Shahar speak right now.
Are you ready to present yours? Then we'll take you first. Okay.
Yeah, sorry.
Thanks. That helps a lot.
Don't do that now. Alicia's going to start editing her slides.
Yeah. So that's one.
Yeah, basically, and we have unfortunately a rule because of the camera about standing in the pink box.
Oh.
Okay, so hello everyone. I'm Bano. I'm a postdoc in the Information Security Group at University College London. And I'm excited to be here today to talk about ChainSpace, a scalable smart contracts platform that we developed at UCL. This is joint work with Alberto, Mustafa, and George at UCL, and Dave at Constructive Proof. So blockchains have exciting applications, but they scale really badly. And also, existing systems do not support privacy-preserving transactions. So given the three properties of supporting flexibility through smart contracts and scalability and privacy-preserving transactions, existing systems support only a subset of these properties. So ChainSpace makes two key contributions. The first is that it supports scalability, and it supports privacy-preserving transactions. So here's a roadmap of my talk today. I'm going to start by providing an overview of the system design. Then I'm going to move on to explain how it supports privacy by design. and then how it supports scalability. Then I'll talk about the security properties of chain space. And finally, I'll discuss performance. So the basic unit of data in chain space is an object. Nodes in the system are grouped into different shards, and different shards are responsible for handling their own objects. So what is an object? An object in chain space holds some state. For example, it can be a bank account, a train seat, or a hotel room. States within object is immutable. And an object can have two states. It can either be active or it can be inactive. Now, smart contracts in chain space represent a special kind of object that has executable information about how to manipulate different objects. An interesting feature of smart contracts in chain space is that smart contracts are composable. This means that procedures in one smart contract can call procedures within another smart contract. So it allows the creation of libraries where these libraries can be used as utilities to compose higher level smart contracts. So how is it decided which objects will be handled by which shards? So this decision is made by the smart contract creator. This is interesting from a regulatory point of view because this empowers a smart contract creator to specify, for example, that it wants its objects belonging to its smart contract to be only handled just within shards inside the EU. Transactions in chain space are a specific instantiation of smart contract. Once a transaction is accepted into chain space, all its input objects become inactive, and all its output objects are born, as in they become active. So for example, imagine that the object is Alice's bank account, which has a balance of 10 coins. Now Alice submits a transaction to chain space to transfer 5 coins to another bank account. If the transaction is accepted, then the object corresponding to Alice's previous bank account with a balance of 10 coins becomes inactive, and a new object is created which represents the current balance of 5 coins, and it becomes active. Now I'm going to talk about how chain space supports privacy by design. So in chain space, corresponding to each smart contract, there is a checker. Smart contracts are only executed on the user side, while the checkers are run on chain space nodes. Checkers are pure functions that only output a binary value, that is yes, accept the transaction, or no, just reject the transaction. But the key property here that a checker does not require any secret information. All it needs is necessary information to empower it to validate if a transaction should be accepted or rejected. So this is in contrast with existing systems in which users have to submit the transaction as well as any secret input required by the transaction to the infrastructure nodes. So this basically means that all the nodes within the infrastructure, for example, Bitcoin or Ethereum or whatever the system is, get to see user secret information, which is clearly bad from a privacy point of view. So what happens in chain space is that a user locally executes the smart contract by providing some input objects, some secret information, and the smart contract executes this transaction and creates certain output objects. Now note that all of this is happening locally, so the secret information has not left user's site. The user then submits the transaction as well as the input and output objects, but only a proof to prove that it possesses the secret information, but not the secret itself. The checker part is then run, which verifies the transaction and accepts or rejects it. So to clarify this, here's an example of an application that could benefit from this kind of distinction between checkers and smart contracts. So imagine that a person wants to run an e-petition within the participants or citizens of London, but it wants to do it in a privacy-preserving fashion. That is, it does not want to know the precise identity of the citizens of London, yet it wants to be sure that participants are actual citizens of London. So how can this be implemented in chain space? Well, the user locally runs this transaction, which is basically casting a vote, by submitting input objects and the secret information, which in this case is its ID, maybe that it is a citizen of London, and creates an output object. Then it submits the input and output objects and a zero-knowledge proof that proves that it is a citizen of London to this checker. The checker verifies and accepts or rejects the transaction, which is casting the vote. Next, I'll talk about scalability of chain space. So the issue of scalability is deeply related to that of consensus. That is, how do nodes in chain space agree whether or not to accept a transaction? So this has two elements. The first element is that how do nodes within a shard agree whether a transaction should be accepted? So we achieve this using existing Byzantine fault-tolerant protocol, which guarantees safety. That is, as long as there are 3f+1 honest nodes within the shard, a common sequence of actions would be agreed. And the other property is that of liveness, that this agreement would be eventually reached. The other element is that of intra-shard consensus. That is, imagine that there's a transaction that consumes objects that reside on two different shards. Then between them, how do the shards agree whether this transaction should be accepted? So here's an example. Imagine that Alice wants to book a hotel room as well as book a train seat, but the hotel room objects are handled by shard 1 and the train seats are handled by shard 2. So Alice wants both the room and the train seat to be booked, or none of them. So in chain space, we achieve this using an atomic commit protocol, which means that a transaction is only accepted if all the concerned shards agree that it should be accepted. Otherwise, it is rejected. So we combine these two elements into a distributed consensus protocol, which we call SBAC, which combines Byzantine agreement for inter-shard consensus and atomic commit for intra-shard consensus. Now, SBAC enables scalability because of two key features. The first one is that only shards that manage the objects concerned with the transaction are involved in the consensus process. And second, these shards can reach consensus in parallel. Next, I will talk about security properties offered by chain space. So the threat model here is the same as that assumed by existing Byzantine fault-tolerant protocols. That is, as an honest shard is one in which there are 3f+1 honest nodes, and a malicious shard is one in which there are more than f malicious nodes. So given this threat model, chain space offers the following four properties: transparency, encapsulation, integrity, and non-repudiation. And I'm going to discuss these one by one. So encapsulation is related to smart contracts that we've already discussed. The key idea here is that a smart contract cannot interfere with the objects created by another smart contract unless that contract allows it. The other property, that of integrity, we also discussed when we talked about SBAC consensus protocol. That is, chain space will only accept valid and non-conflicting transactions. The third property is that of transparency. That is, anyone can authenticate the full history that led to the creation of an object. So let's look at this in a little more detail. The way objects and transactions have been designed in chain space, this naturally leads to a directed graph, right? a transaction creates certain objects. Those objects become active. Then another transaction comes along and consumes those objects, and so on. So you can imagine that this is a directed graph. This graph is also acyclic, because remember that we said that an object, once it is consumed by a transaction, becomes inactive, and no future transaction can again use that object. So this forms a directed acyclic graph. Now every transaction has an ID, which is the hash of all input information that goes inside that transaction. And every output also, every object also has an ID, which is the hash of the transaction's ID and the object itself. So I hope it is now clear that given an object and its ID, it is possible to verify all the history that led to the creation of this object. The last property that I'm going to talk about is that of non-repudiation, which means that if a shard becomes malicious and starts to misbehave, then this misbehavior is detectable. Now, this is possible because chain space offers auditability by design. Every node in chain space maintains a Merkle tree of all the transactions that have been accepted or rejected. And then periodically, nodes within a shard agree whether to seal a checkpoint into a hash chain. What is this checkpoint? It is the hash of the head of the Merkle tree and the head of the hash chain. And the nodes agree whether or not this checkpoint is valid. And if they do agree, then this checkpoint is sealed into the hash chain and becomes the new head. So auditing then involves re-executing all the transactions and checking the results with the hash chain. Finally, I'm going to talk about performance of chain space. So we implemented the SBAC protocol in Java, and it is based on an existing open source library called BFT Smart. We also developed a Python contract simulator environment to enable developers to locally write and test chain space smart contracts and checkers without the need to actually run them on the chain space infrastructure. And all our code is available as open source software on GitHub. We evaluated the performance, especially the scalability and latency, by deploying chain space nodes on AWS. We first evaluated the scalability claims of chain space. In particular, here we are looking at how does throughput of chain space improve or degrade as we add more shards to the system. So here on the x-axis, you can see the number of shards where there are 4 nodes per shard. And on the y-axis, you can see the throughput in terms of transactions per second. So as you can see, chain space offers linear scalability. So for example, at about 3 shards, it offers 100 transactions per second. And at a maximum of 14 shards that we tested for, it reaches a throughput of 350 transactions per second. One thing I'd like to mention here is that we used the BFT Smart implementation of BFT, which is based on PBFT, and offers the same communication complexity, that is O of n squared. So increasing the number of nodes per shard here in our case will not lead to dramatic improvement in throughput. However, there are recent proposals which are more efficient in terms of communication latency. For example, Bizcoin, which was published in Usenet Security in 2016. So if we replace PBFT or Smart BFT, which we use as a black box in our implementation, we can achieve much higher transaction throughput. But the key point here is that our system is linearly scalable. Next, we evaluated client perceived latency, which means that from a moment when a client submits a transaction to chain space, how long does it take for chain space to actually execute the transaction? So here on the x-axis, you can see different loads for the different client perceived latency in terms of milliseconds. And then On the y-axis, you can see the fraction of clients to whom this latency corresponds. And then we tested this latency for different system loads. And we find that even under high load, that is 200 transactions per second having to be handled by chain space, the latency is about 1 second for 50% of the clients and about 2.5 seconds for all of them, which is quite low. So I don't have time to go into the details of the applications that we built on top of ChainSpace, but you can read about those in the paper, which was recently presented at NDSS. In particular, we implemented a privacy-preserving smart metering application on top of ChainSpace, and also a privacy-preserving platform for decision-making. And the paper also includes benchmarking and evaluation information for these two applications. So here are 4 questions for future work. The first 2 questions are related to the auditability of ChainSpace. So ChainSpace is auditable, right? It's possible to detect which shard is malicious. But what of that? Once it has been detected, how can we recover from malicious shards? The second question is that how can a smart contract creator avoid for its objects to be handled by malicious shards? The third question is that how do we map nodes to different shards? Is it just a random process where a coin is tossed and node just ends up in any shard? Or can we use a more intelligent policy for mapping nodes to shard? And finally, and this is a question that is shared by all open peer-to-peer systems, how do we incentivize nodes in ChainSpace to continue to participate in the system and remain honest? So to conclude, I presented ChainSpace, which is a smart contracts platform. Its 2 contributions are, number 1, it is scalable, and secondly, it supports privacy-preserving transactions. It is scalable because of sharding, and it offers privacy because of the distinction between the smart contract part and that there's a checker part which is only run on nodes. So on that note, I conclude. Thank you for your attention, and I'm happy to take any questions now.
Thank you, Bano.
David Mazios from Stanford. I was curious, it seemed like you were claiming that that PBFT is a scalability bottleneck for throughput, not just for latency.
I mentioned that PBFT has a communication complexity of O of n square.
Right.
And we use PBFT within for inter-shard consensus, like consensus within the shard. So we inherit its communication complexity, O of n square.
But you can amortize that over arbitrarily many transactions, right? So I'm confused why that would be a bottleneck for throughput.
It would be a bottleneck, for example, if you had only 1 shard or 2 shards in ChainSpace with a very large number of nodes per shard. But if you had a reasonable number of nodes per shard, then you can achieve scalability by increasing the number of shards rather than the number of nodes within each shard.
Yeah, I guess I'm confused. If what you're trying to optimize is transactions per second, which you may want to optimize more. So I agree it'd be extremely inefficient to run PBFT with 100 nodes. It would be like insane, but you could still run it once a day and agree on 40 million transactions in a batch, right? The PBFT itself can be amortized over arbitrarily many operations. So it may add latency, but if that's becoming a throughput bottleneck, then you might want to look at batching.
Yes, so that's one thing that we didn't test in our evaluations, but another way to improve throughput is to increase block size or the number of transactions that would be batched in a single consensus round.
Hey, Corinne from the Internet Institute. So I had a question going back to some of the issues that you raised going forward. And from the paper, it kind of seems that in the end, you're sort of the benevolent dictators because you assign the shards. But how do you then go to an actual open infrastructure model that is properly trustless? Because that doesn't seem possible with the current mapping.
So your question is not clear to me.
So can you address some of the answers that you have to the questions that you yourself raised
Yeah.
in terms of how can you actually develop this going forward?
So I think I'm not able to use the clicker again.
Sorry. No, try again.
Yeah.
So you mean these questions or these ones?
Yeah. Well, the dishonest shards to begin with.
So we do discuss in the paper some possible options, but those are really bad options. So for example, one option would be to just fork, right, and just exist, start living in a different universe. But forking already exists in existing systems, and it's not the best solution. This is an open question, really, not just for chain space, but all systems, how to deal with malicious shards or disagreements in the system. Thanks. Thanks.
Diego Lopez. The question is related with that. I mean, maybe I have missed anything. The question is very naive, but I see that here the assignment of shards and the decision of how shards are, I mean, how you create a shard and how you split the shard is something that has to be taken by someone, by a central authority, or is something that is decided by the nodes themselves, something that was not clear to me.
So for now, in the existing implementation of chain space, the smart contract creator itself specify which shards it allows to handle its objects.
So the smart creator has to know about the shards, the existing shards.
So information about chain space shards, like the whole infrastructure, would be available in some directory service or somewhere. And these will be like in a rich ecosystem, these will be maybe well-known entities with different levels of trust. So a smart contract creator can specify which shards it wants to allow to handle its objects. So for example, I mentioned that for regulatory purposes, some smart contract creator might want their objects to be only handled by shards located within EU.
But if I don't like any shard, can I make the system create one just by demand, on demand? Or I mean, let's assume I want to create a smart contract. I don't like any of the shards available for whatever the reasons. So can I create a shard? Can I ask the system to create an independent shard, or this is something that is decided?
It is an open system. So if you don't like any of the existing shards, you can create your own shard.
And then the nodes will apply for the shards.
Yeah, and then specify that your smart contract will only handle objects on the shard that you created. But then it's not just you, right? Because a shard comprises of different nodes.
No, exactly. That's
what assuming that you also control all of those nodes. Yes.
Yeah. Okay. I think this is a little bit open yet.
Hi, Jordi Pellicer from UPC Barcelona Tech. Do you think you can scale up to thousands of transactions per second or tens of thousands? This chain space could do it?
So the evaluation that I showed, the key takeaway of that evaluation, I would say, is not to focus on the absolute number of transactions per second that chain space is able to handle. And in fact, in general, that's not a very good metric to assess the evaluation of a system. For example, there are systems that report thousands of transactions per second in their paper, but then they also have hundreds of nodes in that system, right? So as an academics in our evaluations, we can only provide a limited number of nodes. But the key feature is that of linear scalability, right? If you have linear scalability, then the more nodes you add, the higher throughput you get.
Okay, thank you.
Thanks.
Okay.
Okay.
Thank you very much.
Thank you, everyone.
So, Alicia, your slides don't render well in Keynote. Can you use your laptop? Thank you. I don't have this.
We don't have Word.
I think someone has adapted. And it's a difficult task for that area. It's hard to get slides. The part is very straightforward. Yeah, so. Yeah. Where do I project my slides, right?
So you have mini HDMI, or yeah.
I only have this old left. Mic.
VGA. That. Ah.
Wow. Yeah.
Oh.
She has HDMI. Yeah, thank you.
They can put it here.
Yeah.
It's good.
Yeah, she gave him
So let me
PowerPoint,
just
but
get start talking.
just now.
We talk about distributed transactions of solar systems. This whole thing is still just we submitted a research proposal in collaboration with this with a small startup. Huh? Oh, cameras over there.
Can we just?
I need to. I don't need to be on camera, right? As long as people can hear me. Just forget it. Just forget it.
Well,
Let's go on to the.
We can press forward for you.
Huh?
We can adjust that in our slides.
It's not sending the signal.
Or we give you the clicker.
So yeah, this is a proposal collaboration. Okay, and you can draw it. Sure.
Yeah.
Okay. So we just submitted this proposal to DOE, and how we get collaborate with this open solar. That's a story I'm going to tell you later. So go next slide. I need to give you a little background about open solar. I assume that nobody in the room has ever heard about it. So this is a startup funded by US DOE. DOE had this sunshine program promoting the deployment of a solar system, where in California, of course, there's a big business. So what's special about this Operant? They developed their own solar gateway connecting your rooftop with the network. What they use is the cellular link go up to the grid system. But the question is how you collect data from the homes. Normally, people would collect the data use the home Wi-Fi. But there has been known fact that the Wi-Fi sometimes fails. You change your home router, that cut off the solar on top of your roof. So therefore, they developed this, they use this called a LoRa as a backup. So therefore, you can utilize Wi-Fi when this exists. Otherwise, they'll connect your home through LoRa. So therefore, it's a very expensive residential system and at a low data rate, but it's more than adequate for the solar network communications reliably and securely with the power grid system. And the most unique feature of this system is that it's purely implemented with NDN, named data networking. So I think I see Jeff Thompson sitting in the back, and he actually has been helping with the development of this system. They actually have the operational box ready. They have done successful demonstrations in some large scale. Now the question is why they implemented it over the NDN. I tell you the story, go next step. So one day, just about 2 years ago, I got a call from some stranger saying that, can we visit you to learn about how to use NDN? I was surprised to say, how did you even find NDN? Very few people under the sun have heard that name up to this point. They wanted to build this rooftop solar system as a mesh networking. And they looked at the existing protocol stack and felt that way too complex. And somehow Google pointed them to NDN. So they want to come to visit us. So they came down, visited us. They immediately liked the idea, and then built their whole thing on NDN. Then you can see the difference. So we haven't come to NDN IETF to give an NDN talk yet. We will, but not now. Go next. So what's new in this new proposal? So we have been working with them to build that system, moving to the operations. What's new this time is that we want to add this blockchain-based system to build a distributed transaction. So everyone knows that the power system security is so important, and the solar is attached to the power system now. How you ensure the security and everything is just top priority. Now, what's good about utilizing distributed transactions? That basically create a permanent record, readily accessible to everybody, about both the logging of your energy transactions as well as other incidents in the system. Just create permanent record. You know, the home users really wanted to know how much they have contributed, whether the power system actually credited them with whatever the contribution they have made, and also all these other incidences. Anyone wants to make it available, so it's right there. And therefore, of course, we have the expectation that once we make this available, it will be a big improvement to the existing system. The existing system, I don't know all the details, but I have heard the anecdotes here and there. There's all sorts of issues about keeping track of the record, right? There's the human errors, there's other things, and of course, there can be malicious attacks. Erase the record, change the record, and other things. So if we utilizing the blockchain technology, we hope that we can really overcome the existing problems. Go next slide. Now, we're not using the blockchain as a one chain. Instead, there's this thing called ALDA. I'm pretty sure many people have heard of this, especially in Europe. I think it's better known in Europe, in US, that's what I told. This next generation blockchain is not our claim. That's what the elder people claimed. So we just copied it there. Now, so you can see that this is kind of a parallel. Therefore, it's more scalable. They claim that they have a lower proof of work workload, and they can survive offline periods when still adding to the transactions. Go next step. So what are those blocks? You can see the gray blocks to the edges. I mean, the leaf node is just the new blocks being added. The red blocks are those that has been verified by some, but not completely proved. The green ones are completely proved. So go down. The red ones are been endorsed by some, but not entirely. And the green ones actually has been endorsed directly or indirectly by all the gray nodes. That is, the system has accepted them as permanent transactions. So this is how the ALDA works. Next slide. So basically, the 3 steps. When you want to make a transaction, you sign the block just like you normally do, even with the blockchain. Now, the tip selection. So the blocks that had not been entirely proved, you pick one of those. You have to pick at least 2 to add yourself onto it. And now how you pick, that's where the math came in. I'm not going to go through that. Basically, that math proves that if you do this kind of MCMC, this Markov chain Monte Carlo selection, then you can create this connected coherent mesh graph. But for the original ALDA, they still have this so-called reduced proof of work. Nevertheless, everything is anonymous, so therefore they still need the proof of work to allow you, in addition to attach to 2 previous tips, they still allow you to, you have to do this proof of work to add yourself onto the chain. Go next slide. So now, what we propose to do is to get rid of the proof of work entirely. For the IoT systems, you know that power, everything is precious. So therefore, instead of a proof of work, we're going to do proof of authenticity. It is very appropriate for the use case here, because when your home contributed into the power grid, you want to know exactly how much you contributed. It's not credited to your neighbors. So therefore, the use case itself requires the identity, and you authorize that identity. I mean, proves that how much it has actually contributed. And the fact is that the operand boxes is already running NDN, and the NDN already gave every node identity together with the certificate. Because, well, for people who haven't heard about NDN, NDN essentially name the data and use that to network. So therefore, every node, every packet has a name. And because you have a name, you have contents, you just sign it. So by design, NDN packets is cryptally secured. And that is just naturally become the transaction. So there is a strong synergy between the existing NDN product that they have and with this proposed POA-based distributed ledger. So the plan is we try to integrate these two together. I'll go next slide. So how would this operant Solr-based distributed transaction works? You do the same thing, MCMC selection from this Alta distributed mesh. You pick two tips, and then you just create an NDN data packet. You put everything you need to into the contents and send it, give it a name. That's NDN packet. And then you add to the Alta mesh. That's it. The beauty, besides that, we just have NDN with a name and with the security already, that's by nature. In addition, that NDN has the multicast delivery built in. In addition to that, there is another NDN utility called distributed dataset synchronization. Normally, we just call it NDN sync. So you can think of, for the current protocol stack, you have IP as like a reliable, not reliable, unreliable datagram delivery. You have application that want reliable data delivery. So therefore, you have this so-called transport. Well, TCP has been that, and now we're working on QUIC, right, to bridge the gap between what the network delivers, that is datagrams, and what the application wants. That's what the transport is. If one day I come here to give the NDN tutorial, you're going to see that NDN doesn't have a so-called transport protocol, i.e., there'll be data packets created by application, and that is the exact packets that will be delivered by the network. But then nevertheless, we still have the same issue for what the network delivers, which is still datagram, because datagram tells us it works. And what the application wants, which is reliable delivery. And the majority of the cases, we're doing really kind of a group-based applications these days. Rarely, you only have one client talk to one specific server. You know, think about the servers or replicated and all the other cases. So NDN developed this sync that is allows group of entities working on the same application to maintain a consistent data set. Now, what that is what's needed for the blockchain technology. So this all built in. Go next slide. So the unique feature, I think this is my last one. So that this is a Open Solr added advantage because they built their box. So therefore, the distributed ledger actually going to implement it right on the box where data get produced. There have been a number of proposals about applying blockchain technology to IoT systems, like ALDA. I think specifically the IO, I believe, stands for IoT, stands for IoT. I use the name. But the thing is that mostly you actually collect the data and send somewhere where the transaction gets created. And then here in the Open Solr system, the ledger got directly implemented right at the point of data collection. And other things already mentioned, right? If you build a pure NDN system, there's no addresses, and you don't have to depend on external means to assure that all your transactions get distributed to all the other nodes in your chain or in your mesh, because NDN already support multicast, already support data synchronization. I think that's the end of my talk. I believe that our collaborator, Open Solr, I did another kind of little demo-ish thing to show that their mesh network actually works, but that's not exactly related to this topic. So my last slide, if you upload it to the yeah, so this will be the demo, but we don't have to show it here. That's the end of my talk. Thank you.
Yeah, thanks for bringing this work to us. Any questions?
No questions. Great. It's just our proposal so great. No question, otherwise nobody understands how it works.
David Mazier, Stanford. So I'm curious about the motivation for why blockchain helps in the security of the grid. Like, why do you actually need the blockchain or the append-only log here?
Why you need the wall chain? I mean, distributed transactions.
So you're saying that in your first slide you were talking about how there was a motivation for blockchain because the electric grid was coming under attack or whatever. But I didn't follow why blockchain helps defend the electric grid.
This is not, this solution address the power grid security, but rather it's a one step so that you create a permanent logging for all the activities.
Right. So why is that permanent log important for the power grid is the question.
So you keep track of things. You can really go back to
Are we worried about Russians bringing down the power grid, or are we worried about people not paying their electric bill or something? Like, well, what's the actual threat?
It's to log all the events. So I mentioned that we're going to log both the power transactions. This is really to satisfy the need for both the end users and the power system.
Is this for billing or for forensics?
Both.
Okay. So we think there's like billing fraud because of like Enron and things
There
like that.
are definitely record errors. So this way.
Thanks.
Wes Herdiker, USC ISI. Does your client have any? So you said that it takes less power than like typical blockchain. If you look at a lot of voting blockchains, they take way too much power. I assume your client, being an energy company, has some power requirements. Have you looked at comparing, multiple solutions in order to figure out which one actually consumes the least amount of power, and who's paying for the computations at each of the nodes? Is it the client or the power company?
You understand that we are the operating solar gateway actually is connected, I believe, to the power grid. What they measure and collect is really about the rooftop solar generation. It's not they depend on that solar generation to operate. That's one thing. But the second thing is that, no, I want to be honest, that we haven't done any comparison, but just that intuitively, if you do a simple signature verification, it should be cheaper than all this other proof of work. There's additional things about proof of stake that was developed recently, but that I think has other issues. It's not the power assumption, but rather it's really, if you are rich, you get richer. And that, I wasn't sure it's a desired property.
One simple question. A lot of IoT devices have a limited CPU capability and just say the battery consumption and limited memory. I don't know whether this solution you propose can be used for such limited capability IoT device. This means how your solution is capability.
I'm not talking about a general solution for IoT under the sun. This is a specific solution to secure the solar data collection system. But I will add to say that we have done work about using NDN to support IoT. There's a toy code here and there. Again, Jeff in the back probably knows more than I do.
that you think about the IoT, you think about if you use IPv6, there's plenty of addresses for sure. But the address assignment, you have to communicate application semantics by first translate into addresses. Well, I showed that comparison of protocol stack. I think that speaks for itself, right? The application want semantically meaningful data. It has to be secured. And so see how many layers we have added to reach from the lower IP packet until up to meet the application requirement. And the NDN basically removed that gap. We communicate directly using application name and secure it. But again, I don't want to talk about NDN here. We will one day.
Okay, we are also running a bit late, so thank you very much, Lisha. So next will be Dino on a decentralized mapping system for Lisp. Do you still want to use your iPhone? Or? Yeah. Okay. Is the cable long enough? Okay.
He said anything about their problems with the blue cache function or IO.
Yeah.
Yeah, there you go.
Okay.
Okay, this talk has nothing to do with blockchain. We're going to talk about a decentralized mapping system for overlays called Lisp. So the problem statement is, what if Lisp XDRs didn't need to depend on a third party? So Lisp is a protocol architecture that's been around for about a decade. It's an overlay solution that maps EIDs to locators, so EIDs can remain fixed while locators change. An XTR is a data plane component of Lisp, for those of you that don't know Lisp. So what if Lisp XTRs didn't need to depend on a third party? In other words, a third party that operates the mapping system between EIDs and locators. What if Lisp XTRs could multi-home and roam to inform each other about their RLOC changes? An RLOC is a routing locator. A locator is a topological significant address that's in the underlying routing system. What if Lisp XTRs could be their own mapping system in a peer-to-peer fashion? Let's build a purely democratized and decentralized control plane, and that's what the talk's about. So throughout the presentation, wherever you see green, we're talking about endpoint IDs, and wherever you see red, we're talking about routing locators. These are not topologically significant. They could be opaque, they could be public keys, they could be random numbers, they could be selected however you want. And routing locators are topologically significant, they are aggregatable, they are in the underlying routing system. Okay, so let's just describe real quickly what today's mapping system, how it works in Lisp. So basically, these XTRs are these data plane routers that basically bridge the EID space, which is part of the overlay, to the underlying internet. This is showing an example where there's 4 sites. Let's say the east and south site is using the mapping system on the right, and the north and the west is using the mapping system on the left. They're separate mapping systems, which means they register and they request RLOCs for the ones that they're registered for. So really, east and south can't really find the locators for north and west. Okay. So it turns out that the mapping system is very much like DNS. It's in the infrastructure, so you depend on it. You depend on it, you might have to trust it, you usually do trust it, and it usually gives you good answers, but not always guaranteed. But it turns out that a lot of topologies show that maybe this south and east site has backdoor connectivity, just like the north and the west site. Maybe there's some wireless infrastructure there. And what happens is, let's see if I can do this fast. What happens is, what if the links to where the third party is go down? Now, it turns out that the sites could still talk to each other, but they don't have a mapping system. They don't even have DNS either, right? We still want them to function. We still want them to roam. We still want them to be multi-home. Okay. So the way the mapping system works today is Lisp control messages are sent to map servers that reside in the infrastructure. And this is an example here where we have an IPv4 EID space, and this Lisp router basically registers to two different map servers in the infrastructure. The 3333 and 1111 are actually in the infrastructure in the routable space. And the right just shows an example where there's an IPv6 EID prefix where that XTR2 is registering to two different map servers, part of a different mapping system. Okay. So how do we take this model and make it distributed? So can we have a decentralized map server? What if each XTR itself was a map server? What if each XTR could map register to each XTR? The mapping system would be synchronized because everybody's talking to everybody. Very similar to like a routing protocol, but it's really over the top. Okay. And the XTR could actually be a map resolver for itself. So when it says map request, it doesn't have to go outside. Since the databases are synchronized, it could just do the map request locally. So let's define how this decentralized mapping system could look. A consolidated mapping system is identified by a multicast group address. Okay, let's say that the map server is a multicast group, not an individual IP address. The XTRs that are part of the mapping system join the same multicast group, and the map registers are sent to the group, which means all XTRs receive all mappings. It's sufficient distribution when the underlay supports multicast, because rather than one router sending N packets to all the other XTRs that are part of the consolidated system, it sends one message and the underlay delivers it efficiently with IP multicast. When IP multicast is not available in the underlay, we can use head-end replication. We have something in Lisp called signal-free multicast where we use the mapping system to store SG entries, and we find out who the receivers are and where the members are located through the mapping system. So we could actually iterate and use the Lisp data plane to simulate multicast on the overlay if the underlay doesn't support it. So here's an example how it could work. The guys on the west-hand side are part of the same mapping system. They're not involved. They're the odd routers, 1, 3, 5. The ones on the right-hand side are 2, 4, 6. They're completely separate. Let's say they have no connectivity to the internet, but they could still talk to each other. This would be an example how it would work. They're all part of the mapping system. They each have their EIDs 1, 3, and 5. They register to 224.111, which is a multicast group. They're all joined to the multicast group, so they all receive each other's registrations, so they all have a synced copy. The right-hand side is the same thing, it's just using IPv6. Of course, you don't have to have separate IPv6 in v4 mapping systems. They could all be merged and you could have different types of EID types. So benefits, XTRs only depend on each other, and they already depend on each other because they want to talk to each other. There's no third-party trust or dependency that exists. The map request lookup has very low latency because it's just a map request message that you can loop back to yourself, or if your implementation wants to access the data structure directly, it could be even faster. XTRs build and send one map register for end XTRs because of the multicast group joining capabilities. Also, everybody in some consolidated mapping system will discover each other just by joining the multicast group, so resource discovery is just automatic. Management is simplified by accessing one XTR to get all mappings, kind of like a linked state database. If you want to know topology, you only have to ask one router. The same thing here. You just go to one XTR and you can find all the mappings. It turns out an XTR could be part of multiple mapping systems just by joining multiple multicast groups. And this pretty much has the same benefits as any peer-to-peer networking application where things are, you just depend on each other and you use each other's resources to move forward. The high-level use cases that we think this will be useful for is to be consistent at the network layer with decentralization as we are with cryptocurrency applications. So if peer-to-peer networking is going on for cryptocurrencies, we think we could do it at the network layer as well. Emergency networking or mesh networks is very important. You know, what if you lose power? Emergency hurricanes, earthquakes, or whatever, this is very useful. Wi-Fi Direct on cell phones can make use of this sort of technology. and people could still move around. You know, when there's an emergency, you're moving around quite a bit, and you may have LTE or 5G access in the future, but you may not. So you're hopping around between Wi-Fi hotspots, and so your IP address is changing. Your RLOCs are changing. You want that binding to be known to everybody that's relatively in signal range so you can keep talking to each other. We think this is going to be good for plug-and-play VPN networking, right? But there's a lot of container-based microservice, microsegmentation type applications that just want to come up, do ls-l and shut down, and they may want to talk to each other. So rather than having to configure or go really far out to get your mappings, which require additional latency, you could do this stuff locally. Space networking, software-defined satellites. You might want to do things up in orbit because the distance from space to down here is pretty far. Shareable economy apps just in general. I think Paolo made it, or I think you made the comment about you want a sort of reward for doing work. So you want the cost of running the network to be low. So you want to be able to share bandwidth, CPU resources, all this when you don't have internet connectivity, but you do have network connectivity. So we did an implementation of this, and here's just a brief demo. We had 3 containers, each running Lispers.NET XTR. That's my implementation. They were running in the Docker containers, but the Docker bridge was not doing multicast. So we wanted to show that the underlay did not support multicast. So the XTRs were doing head-end replication in their data plane. And then the XTRs were registering both an IPv4 EID prefix as well as a name EID. If you wanted to, in this emergency situation, and didn't have DNS, you could put names in the mapping system, and the names could be resolved to EIDs. So this is just an example in N1 is one of the containers, the first one, that you see EIDs being registered for 1/32, which is N1's EID and its name, and you see 2 and 3 are also there. If I just look at the next one, they're all just going to be synchronized. Now you see this special entry here that's called 0/0, 224/4. That's actually the mapping system saying it'll allow anybody to join any IPv4 multicast group. And it turns out since this mapping system is running on 224.111/32, that contains the information of all the members of the group. This is part of signal-free multicast. What it means is that 224.111 says, here are the 3 routers, and those are the RLOCs of the underlying network. Those RLOCs could be IP addresses that are on Bluetooth interfaces that allow 3 phones to be able to talk to each other. Okay. So that's what's in the mapping system, and this is in one of the routers, showing that for a particular forwarding entry, if a map register is coming down from the list control plane to the data plane, it matches this entry, it'll replicate to those 3 unicast addresses. That's it. Questions, comments?
David Mazier, Stanford. This is pretty cool, but I'm wondering what prevents someone from setting up a malicious XTR that starts hijacking EIDs?
So we sign all map registers that go to the mapping system. We have a draft that does EC DSA. So when you register these mappings, you have to sign the map registers. The public keys are also stored in the mapping system.
So now you're assuming, so the EIDs are now public keys, or what are the public keys?
If the EIDs are IPv6 addresses, and that's what you're using for the applications to communicate on, then they could be using these crypto EIDs. But you can create crypto EIDs for the sole purpose of registering other types of EIDs, like IPv4 names or whatever.
But then how do I know if I'm about to, delegate my EID to an XTR for an hour, and I presume I just learned that of that XTR by multicasting or something?
Yes.
So how do I know that's not like the equivalent of a malicious DHCP
to
server
join
or
the
something?
multicast group, you have to register your RLOC to that multicast entry, and to register it, you have to sign it. So you can actually control the members who are joining the multicast group as well.
Sorry, I was assuming that I'm here in London, I open my laptop has some EID.
Yeah.
It tries to find some XTR nearby.
Yes.
How does it know that that's a real XTR and not something that's trying to hijack my EID?
Your application is going to want to know that you want to talk to an IP address that's running with that XTR. And And since you start sending packets to it, what you're going to do is you're going to try to find the routing locator associated with that device, right? That thing must be already registered to the mapping system and must be authenticated to be admission control to the system.
There we go. So who's then authenticating the RLOCs?
The-
Is that
so-
still centralized?
The way authentication works with map registers is when you send a map register to a map server, you sign the map register, and then the map server verifies the signature by looking up the public key. And it looks up the public key in a mapping database, which is its own. So at the same...
But that's centralized.
That doesn't have to be centralized. You could use another multicast group. See, anybody could register public keys for themselves. The question is if you use them or not is another story. And those could be made secure, not having the circular dependency of also signing those type of registers.
Well, I don't want to, maybe
We can take it offline if you want, yeah.
Just quick, we're closing the line, so you are the last.
Stefan Bartmeyer of NIC. What happens if some of the message you sent over multicast are lost?
Yeah, so there's multiple ways of handling that. The protocol right now, the standard says you send map registers periodically. They're sent at 1 minute intervals. If you think that's too slow because you want better convergence, there's a want map notify bit in the map register where you get a map notify in response to the map register. That's basically an acknowledgement. And when you run in that mode, it means you will retransmit much faster until you get a map notify. The third alternative is you can just run it over TCP and you get reliability without putting the reliability machinery inside the list protocol.
Okay, cool. Thank you very much, Neil. Did you want to say something?
Maybe mention side meetings. By the way, there's a slide at the end of the agenda deck about this, but we had far more requests for time on the agenda than we had time available. So we've had some people have mentioned the possibility of having side meetings, and we encourage this. So if definitely take it to the mailing list. I know that Bo Yang has expressed interest in discussing PKI on a blockchain, and there are similar applications. So please, as I said, take it to the mailing list.
Right. So for the rest of the meeting, we wanted to get a bit of feedback from you. So so we had a couple of different interesting presentations today, also at that interim meeting. So ranging from ideas for use cases, particular solutions, pointing at problems with, for example, certain ledger technologies, different consensus mechanisms. So what is, could we get a bit of feedback? So do you think, so there is a, say, good topic here that warrants future meetings? Do you think this is interesting, useful? Let's discuss this a little bit.
This is Dina. I'm wondering if anybody has the desire to interwork different blockchains together, or is that a terrible idea?
Actually, yeah, the Ripple folks keep coming to, I don't know if there are any of them in the room right now, but the Ripple folks are working on an interledger settlement protocol, and they've been coming to all the standards organizations.
And
Nick Johnson, Ethereum Foundation. Regarding internet working, there's also Polkadot, which is an effort by Parity Technologies, and Plasma. The challenges largely are that currently they're so diverse and differing in capabilities that it's difficult to build any general purpose system for consensus. But I think that if we can make progress towards that, this would probably be a good venue.
One thing worth pointing out is that we're not really a blockchain group. Right, we're really trying to deal with decentralizing internet infrastructure, and there are various technologies which may or may not be used. Blockchain is an obvious one in which there's a lot of interest. But we probably are going to be working on blockchain protocols per se. We're interested in consensus protocols because of the there are obvious scaling issues when you're talking about something at internet scale. So it's not, we're not really a blockchain group.
There's a blurred distinction between where something stops being just a consensus protocol and starts being a blockchain, isn't it? I thought Stella's presentation was a good starting point for building a generalized, a decentralized consensus protocol that isn't necessarily, I mean, it might technically be a blockchain, but it's used for other purposes.
Absolutely. And in fact, what we're seeing is a lot of sort of naive proposals about the use of blockchains where they're not really dealing with the consensus aspect of it very, very thoughtfully, frankly. And, I also chair the CT working group. In a lot of ways, a permission blockchain is basically a transparency log, right?
Yes.
So,
I mean, for my part, I hope that ZARG finds time to work on better formalizing consensus systems using those sort of technologies so that we can apply them to more areas like certificate transparency.
absolutely. And I mean, one of the things we're discussing right now is what should we be working on. So, we'll be working on the things the participants, bring here.
Thank you.
This is Dino. I assume the RG cares about interoperability at any level, even though you don't want to do blockchains. But I'm thinking of the other thing that's probably useful is today a wallet tries to support all blockchains, and that's not very efficient. So do you think we could standardize a protocol between wallets and blockchains so all the blockchains could use the same interface? And this doesn't mean a RESTful interface, which everybody seems to want to use today.
Well, I mean, we are doing research here. We're not really doing standards, but I think what has, right. But I think what has become apparent is, I mean, that like connecting, federating, these kind of things is a research topic, and it's not entirely clear how this is going to play out.
David from Stanford. This is actually a point that came up at the interim meeting that actually Sydney and Jean-Luc brought up. But there are things that currently, have sort of ad hoc solutions where you have to get, every browser vendor to add you to their, HSTS preload list or something. So I think one thing to work on is taking things that currently are a pain to do and making them sort of self-serve so that you can, basically the equivalent of let's encrypt, but for all these other things you might want, maybe you want, HPKP, you want to be on the HPKP preload list, and there should be some way to get that done for your domain name.
Hi, I'm Faye from the University of London. I think this group's really good at the moment in terms of the consensus side because we're doing some research on proof of work algorithms, and some of the economic research we've done shows if you look at the ASIC miners involved in the SHA-256 hashing, just the capital expenditure on those, if you take the daily hash rates in Bitcoin to be about 10 grand, to be about $4 billion US. So the sooner consensus algorithms sort of decide on something that are used more ubiquitously rather than just script or hashing or SHA-256 hashing, I think that's something really positive because the growth curve for the purchase of ASIC miners has been exponential since the beginning of 2017. So.
Hi, this is Lisha again. I assume this group, if it created, it would be called DIN, right? DIN, not BIN, BIN.
No, sure.
Right. So therefore, I think we should focus on decentralized infrastructure and not blockchain specifically. That can be a potential tool we may utilize, but that still deserves investigation. Nevertheless, I think for decentralized infrastructure, there are other potential solutions, and this group, I would suggest to explore and not limit ourselves to blockchain.
I think that's understood.
This is Marie-José Maupetit, no affiliation. I will follow on to what Lisha said, but for me, I was here today because I thought there were incredible problems when you start decentralizing the internet. I think the idea of the trust and the distribution of the authentication and consensus is fantastic, but there are still people out there who think that the only way that you can make networks being very efficient is to have them under a certain, completely non-distributed infrastructure. So is it going to be part of this group also to see what are the other problems in terms of management, in terms of performance, in terms of all kinds of things that are
very important when you start, blowing up something that is centralized and becomes a bunch of islands talking together.
Yes.
Yes.
Yes,
well,
okay.
So that's a good question. It's not easy to answer because, I mean, there are certain, networking or communication systems. So like ICN, for example, I mean, they have their own group. They probably deal with like the management and self-organization features for their system. So one way of seeing is so everything that has to do with like distributed computing consensus, that there could be some kind of focus point in this group that takes the requirements from all these different networks and what have you, and discuss this here.
Okay, because I actually thought that there was going to be more like, maybe there's stuff done in other groups, but I think that's becoming the problem, is that there's a lot of pockets of people thinking about decentralization in other group, and I thought this one could probably be the focus, and then have more, and I agree that the consensus stuff is very important. But when I think about it, I think also of other things. And if the work is done in another group, I was in ICN yesterday, could this group then become some kind of the clearinghouse for all these different approaches or something? I don't know, I'm asking a question.
So I don't think we normally, I don't think we have a good track record of working with clearinghouses in the IETF. So I mean, we should really, I think, focus on the research questions.
Well, I mean, a clearinghouse in the sense of also a focalized point for the research and people who do decentralization.
So I think
a central focus for decentralization. Yes, I love that.
So I think
there's a Kafkaian or even a Newspeak thing to it.
Yeah. So I think what will not work, I mean, if we make a master plan on, say, how we organize decentralized systems, and so how this group would control this. But I mean, this is really contribution driven. So for example, if there's a topic that has to do with decentralization and has some interesting research questions, please bring it here and then we can discuss it.
Okay, thanks.
Hi, this is Eve Schuler from Intel, and I guess I showed up here. I've shown up here a couple of times now because, well, I agree that the consensus algorithms are really important, but I think the motivating factor for me is that when I look at what's going on in the IoT, there are at least two things that I think we should be addressing. The first is that, yes, we're an organization that worries about connectivity, but increasingly there are lots of things that are disconnected, either intermittently or for long stretches of time. So I like Dino's presentation in that there's this concession that, not everything's connected all the time. And so how do you bootstrap, particularly, I mean, yes, the federation and the directory is super important, finding things, what are their attributes, but then coming back to some of these talks earlier about trust, how are we going to trust the things that we find, whether they're directories or whether they're nodes, and so here's my second point, the other reason why I showed up, which is the Internet of Things creates a tremendous amount of data, and thinking about managing not just nodes and the trustworthiness of nodes, but can we somehow, through chains of trust, we can trust the nodes that in turn create the data, and this goes back to Leisha's talk. You want to be using blockchains to be attesting to the data, the authenticity and the trustworthiness of the data. And so I think that the solar example is quite interesting because once you have trustworthy data, you now can do analytics on the data. Maybe you have trustworthy analytics, and then when you get back to critical infrastructure, you've got trustworthy decisions that you're making. So those are two things I would love for us to work on, the disconnectivity and then this chain of trust, so that when things get actuated in the real world, that we have, particularly for critical infrastructure, that we can, things don't fall apart. So that's why I'm here. I'm hoping we'll have an inventory. Oh, so back to this point that was made right before I came to the mic, which is maybe we don't have clearinghouses, but there's a broad collection of things that we could work on. This could be a great place for people with such disparate interests to come together just to coordinate what they're doing. So maybe it's not a clearinghouse so much as a coordination mechanism.
David from Stanford, I agree with a lot of what you said. I just want to be pedantic that blockchains cannot attest to the authenticity of data. They can maybe attest to the immutability of data, but I actually think it's important to always keep that in mind, because somehow there's this like mission creep where people start thinking, oh, blockchain, it'll solve everything.
Good point.
So Alison Mencken, I'm the IETF chair. I think that we want to make sure that we use the high volume face-to-face time really well. So it's a great time for understanding fundamental problems, really focusing on hard stuff together, learning to talk about hard stuff together. You can put a clearinghouse on the wiki or whatever, but I am very tough on the RGs because I don't want them to have sort of an assortment of stuff that allows you to sort of drift off when it's not your topic. I really want everybody in the room focused on how can we talk better together so we can solve problems better together. And I'd love to see a few outputs that actually demonstrate that sort of progress along a path that has used the time well. So I'm going to be really strict to all the research groups about not making a diffuse discussion. And I think that would sort of answer some of the questions. And this is probably the wrapping up statement because it's now the end of the time. But
Yeah,
I was just going to say that maybe one way to crystallize what we're doing here is, and I know you've done this a few times, is to do this inventory of like, well, what do people want to be working on? And really decide which of those are unique that set this group apart from the things that already exist.
yeah, but so the contribution driven has to be curated because there's so much valuable time in this room. So I'm in favor of saying what do people want to work on, but it's got to be something that's about advancing a problem here, not advancing a problem somewhere else. And I can say that if we have kind of a desire to do our overall, like what is the whole architectural story with all these pieces coming together, that's a kind of natural thing to bring to the IEB and say, can we do 2 or 3 days where we put it all together? I would support that, but I think that's quite a different problem from asking really hard questions and helping the people work deeply on something to get it more applied and further along, which is, I think, a really good use of the time in the room.
Okay, thanks a lot. That was really good input. So what we're going to do is, so we try to digest all these suggestions and try to phrase so a few, so often very concrete topics and research questions that we would like you to help us discussing on the mailing list. Thank you all for coming. It was very interesting. Cool, thanks.
Where are the blue sheets? Excuse me, where are the blue sheets? Hi.
On you?